So to process our LiDAR data, we're going to use a product called LP360. It was renamed to EVO and it's being renamed back to LP360. That doesn't mean much, but it's an application that's set up to process the data. Now it doesn't all operate within the software itself, so it calls out requests to POSPack, which is a separate package to process or post-process your data off of a base station. You'll also reach out and use Metashape's Agisoft to process the aerial photography into a mosaic data set. So this is the first time I've processed this data, so I've got no idea what it's going to look like, and you'll probably see a few mistakes in amongst the video. So I'm going to start off by creating a new project. So I'll show you what data we've got. So here's my package from the field trip. Here's the flight area that I did as a KMZ. Here's the project that I'm working on. So we store the information under TrueView, and this is where our original cycles are. I also tend to take a copy of the core and the system config files these days. When you change these configurations, it has a immediate impact upon the LiDAR itself. So if you increase the field of view under the core configuration file, then it increases the field of view. So it's useful to keep those two files along with your cycle data. And in your cycle folder you'll find two more folders. One is the flight and the other is the system. So it's already got a system and a config backup in there, as well as a flight and event log. So we can open up the flight log, and as you'll see here, it's just a log of everything it was doing as it went through and the time that achieved it. So it checks to make sure that the folders exist. It creates a new cycle to work in, checks the firmware version, the serial number, I guess making sure that we're licensed, and so forth. So as we scroll down through here, we can see different bits and pieces of its original setup, and then as it's working, comes through here. So camera 2 captured image number 6 successfully, and camera 1 captured the image successfully at these particular locations, and that's how far it is from home, and so forth. So you can see each of the bits and pieces of the log. So it's going to use the logs, the path. So if we have a look at the path file, again it's just a series of coordinates coming off of the GNSS. So when you send information from a GNSS system through to some sort of a device, there's a lot of different protocols and ways to achieve it. So normally it sends what we call an EMIR string, and there's different types of variables that can be stored in here, and we can see that this one's picking up the GPGA storage. So here's our coordinates, and as you can see, we need to divide that one by, we need to divide them by 100. So it multiplies by 100 in order to not need to have as many decimal places, because that's becomes quite hungry for data. So there's no columns to tell us what's what, but we know that's easting and that's south. so that would be a negative number when it gets into northing, and we might be picking up elevation information. If we scroll down far enough, we can see that this number is getting higher. So that's data that it's storing in that particular folder. Under the flight folder, we can see that again there's another system. So here's your flight path and flight events. No, we didn't look at the flight events one before. So it keeps a certain number of backups so that if things get changed or lost, it can go back. But this events is purely just a set of values that mean nothing to us, but would sequence in with the flight path, probably the timestamp and a few other bits and pieces. So this is the binary output that comes off of the LiDAR unit, and then under camera you'll see that we've got a whole lot of images taken from camera 1 and the same again from camera 2, and we've also got this TVC file which is information about it. So that's what's in the cycle folder. There's also some other information that I'm going to need. So under Trimble Business Centre, I have a number of files that I needed to process. So I brought in a job file, which was the survey marking, or the ground control points that you guys picked up. And I've got another one called STEM 2003, which was the job that I created. As a part of that process, it generates a TO2 file. So a TO2 file is what comes off the base station, but we need to run it through a process called Rhinex. So Rhinex is a utility. There's a utility to produce a Rhinex output. So if we come under Trimble, we see convert to Rhinex, and Rhinex is the format that's recognised. So we can come in here and open our file. And it's going to go through and scan through the file. It then pulls out information from the Rhinex and gives us an approximate idea of some of the basic information. We can then run our tool. So this is a tool put together by Trimble, and we can log in other controls. So we just want to convert the file. So it's now converting and outputting this set of files here. The only one we're really interested in is the O file. So I'm going to close that up now. So now that I've got my Rhinex file, I just type in AusPos, and this will take me to Geoscience Australia's positioning processing service. So there's a bit to read through here. Please read it because it'll only accept certain files, only accepts in certain formats, and the first time you use it can be a little bit worrying, but it's reasonably straightforward once you get through to the bit that you're doing. So I need to find my project. and now I'll ask it to scan it. It goes through, it's recognised that it's the R10 from Trimble. I put in my email address here and then hit submit, and it will send me a report. I'm not going to submit it because I already have the report. Anyway, so this is the report that comes back from Geoscience Australia from the AusPos GNSS processing. So if we scroll down, there's the standard information. AusPos 2.4 is the current version. A little bit about the data that we sent up. A list of the reference stations that it's going to use in order to do the corrections, and our station is known as Mark. So here's our computed coordinates for GDA 2020, and that's based off the International Terrestrial Reference Framework for 2014 at the 2020. So here we can have a look at the Cartesian. Gives us a little bit of information about the AHD and how it's been computed. The derived AHD is only provided for sites within the extent of the Australian geoid. If we scroll down a bit further, here we've got our latitude, our longitude, our ellipsoid height and our AHD height. So we can see that there's just under a metre difference between the two. And here it is in GDA 2020. We're going to be processing in 94. So this is section 3, we want section 4. This gives us information about GDA 94, which is built off the International Terrestrial Reference Framework for 92 as at 1994. So that's why it's called GDA 94. If we scroll down, here's our Cartesian. Here is our geographic. So that's the information that we need in order to plug that in to give us our starting location to do our geocoding of our LiDAR data. So we'll just keep that open so that we can come back to it later. So now that we've made sure that we've got all the files and data that we need in order to process our project, let's start by creating a project. So I need to give it an out location. So in this case, I'm going to put it into my TrueView. So I need to give it a name. I'll call this one Clip Face, and give it some sort of name, and we need to give it some sort of a reference system. So we're going to choose GDA 94, MGA zone 54, with the Australian height datum AusGeoid 09. So now we just say create project. It gives us a warning letting us know it's going to create a project. So now there's an opportunity to bring in other data sets. So if I've got an existing image, for example, I might bring in it as a raster. If I've got pre-existing LiDAR, or if I want to bring in a feature, I can do that. But we're not necessarily going to be too interested in that. Looks like we've got this artifact on our screen, which is a bit odd. So the first thing we need to do is import our data. So we use the TrueView import wizard. So there's a number of ways to bring in our data. We can import from an existing archive, from a guest fleet. So there's a number of different instruments that you can bring in. So L1 is the DJI LiDAR unit, so if we're using that, we could have selected that one. And we can choose whether to only import our data but not make an archive it, or archive and import cycle. So this is the one we're going to choose. This way it's going to make a backup for us into our archive folder. So in the software I've already designated a folder as an archive folder. So now we can go and look for the input cycle. So if we come in here, here's our original cycles, we just select that one. So now it's worked out where the camera locations are. So now we come in here and we can give it a name. So I tend to keep the codes. It doesn't really make too much difference. I do find that when I've got a lot, that it becomes handy to rename these into something more useful. So we'll describe it. Cliff face. And the site, I'll just call it Onca. And it's already selected the project spatial reference system. So we go to next, and now it needs to know where the base station was and the observation files. So if we click on here, I'm in my correct project, and there's the O file. So when we ran the convert to Rhinax, we ended up with this O file, so I'm able to select that one. So I don't need any auxiliary files. Now I need some sort of a start base station location. So there's a number already in here, we need to add a new one. So we'll call this Onca Cliffs. So I could put in the base station, the survey marker ID in there, but as it worked out in the end, we weren't able to use the survey marker because someone had forgotten to put the plumb bob in. So we just used the GNSS itself to give us our starting location. So we're able to bring in our coordinate system. So our coordinate system that we're bringing in so the coordinate system that we want to work in is GDA 94, and it's the epoch 494, and we don't get to choose. So it's going to use the GRS ellipsoid. So let's put in our coordinates. So our latitude value. So our data came back as degrees, minutes and decimal seconds. So I've chosen to use that one. And now I need to put in the latitude, so minus 35 degrees, 9 minutes, 56.64479. Now our longitude is 138, 28 by 15.47448, and our ellipsoid height. So if you remember, we had two heights. This is the ellipsoid height that we're going to want to use, so we'll drop that in. So we'll say OK, and now we've got a new survey nail or survey marker that we can use going forward. So now we go next. Yep, so this is where our archives are being held. So now we can say finish. It'll pop up a screen asking if you really want to do this, and we're going to say yes. So now you can see that it's importing the cycles, and this process, depending on the flight, can take quite a bit. So I'm going to turn up the music and probably speed up the video a little bit just to get it through a bit quicker for you. Okay, so it's successfully imported the archive of the cycle, so we'll say OK, and here's our flight plans. So it looks like it's taken off from about the right spot, and you can see that there's trajectory points, there's log points, and there's photo points and station. So here we can see a mixture of the orange and the red, so stations and trajectory points, and some green lines of its estimated flight. So let's bring it so it all fits on the screen. Of course, the zoom is the opposite to the zoom in ArcGIS, so I apologise that I'm going to seem to zoom the wrong way every time I do it. So there's a number of steps that we now need to undertake in order to get this data to be useful. So the first step, and they tend to be all on the single tool set. So for now I could hide all the rest of these, but then I wouldn't remember where to turn them, which ones I needed on for later. So the first thing we need to do is our POSPAT processing. So if you remember, we took our file from the base station and we sent it to AusPos, and AusPos gave us an accurate location for where the base station was. It then works out for us off of that location using the Rhinex files and the TO2 files how much adjustment each and every location in the data set needs to go through. And this is right down to each point in the LiDAR point cloud. To our project settings, and here's where we can set up our project information. We can set up some global variables, and this is where we tell it where the POS pack is. So we can go in, so POS pack was downloaded from the Flatnex website. We're currently using Service Pack 1 of POS pack UAV 8.7, and we'll be upgrading shortly to Service Pack 2. So you need to make sure that that path has been correctly entered in before you can start to process. So let's just open up our wizard again, and it's going to go off and generate a TO4. So TO4 is the log coming off of the cycle. So our processing mode is off a single base station. So we could use RTX or we could use Smart Base. We want to run it locally. There is the ability to run it in the cloud, but as you see, we don't have credits for cloud processing. We don't need it because we've got the license for the software. We can tell it to just use the GPS satellites, which is the American data set, or to use all constellations. And it's picked up the details associated with the particular sensor that we were using. So we'll just go to next. We select again that O file, which is now that it's made a copy of it into our processing area. We're using the survey nail, using this one. There's our description, here's the location coordinates, and that's the frame data information. So now we need to tell it what we want out. So we want MGA zone 54. So why are we not using 2020? Well, zone 54, GDA 94 is the projectional coordinate system of the previous data sets. So in order to be able to match the two together, we want to work in GDA 94. So we've set that, and our heights can either be ellipsoid or geoid. So here's our OzGeoid 09. Now when we process the LiDAR data, we processed it using OzGeoid 09. So this will ensure that the data set of our control points will match in with the coordinate system of our data. So we go to next. It's estimated it's going to take around 23 minutes to process it, and we'll submit that. So it's just warning you that it's sending it off to another software, and we'll tell it to create the POSPAC trajectory file. So this is going to take a while, as you see, about 23 minutes. So again, I'll put on some music and speed up the video. So now it's completed that process successfully. So let's have a look at the report. Just give it a minute to come up. Okay, so maybe we won't look at the report. This particular computer doesn't have a PDF reader installed. So we've gone through and we've done our trajectories. So now you can see we've got a trajectory line. So if I turn off these, here we've got our trajectory line. So that's been calculated based off of the information. So our next step is to create our flight lines. So we'll click on that, and here we can make some adjustments. We'll just take the defaults, they will work fine, and that's now done. So you can see now that we've got flight lines and a few little gaps in between. So we're going to want to do a bit of a clean up on our data. There is, for example, we can come in to stations and use the feature analyst to examine our data. For those of you that have been through my topic, I suggest that you become intimate with your data, you get to understand your data. So as I select each of these, it's going to go through and update the images in the little preview. So you can see that the camera has been moving along, collecting more data. There's really not a lot we need to do in here, it's just useful to come in and have a quick look. So if we have a look at our trajectory lines, so we'll turn off our photo station locations, we need to do some fix-ups. So this particular part of the flight was the last return flight. So to clean up, we use this toolbar here. So this is the feature edit toolbar. Not quite like the GIS editor, but it's sufficient for what we need to do. So we're going to get rid of that little line there. Just hit the delete key and it goes away. So there's a few little oddities about the data that we collected. Normally if we were flying LiDAR, we would be flying a grid pattern, and we can go through and get rid of anything that doesn't fit within that standard grid. But we were interested in trying to pick up this cliff face, so we haven't flown a nice smooth grid. So we have a number of options we could process, including this particular flight line, which was the return home, or we can remove it. So for this particular exercise, I'm going to remove it only because I don't want any odd data sets turning up, or points turning up in your data sets. If I had the time to do all the quality control and quality assurance processes on the data set, I might have left it in or processed it separately to see if it's going to actually enhance my data or whether it's going to make it worse. So now that we've gotten rid of the lines we don't want, now we need to plug in bits of line that we might want. So if we have a look here, we've got a gap in our data set. So I'm going to turn on the trajectory points, and you can see there's a number of points that don't fit in. So just to avoid multiple selection, I'm going to turn off our trajectory lines. Once I work out that there are 5 points, starting with this one, hold down the control key and select the other end. So I can turn this back on. No, I've gone a little bit too far. So I'll make it that one and that one, and that works nicely. So you'll find on a different toolbar the tool that we need to generate that particular flight line. So up here on this toolbar we've got a tool called Create Flight Lines from Selected Trajectory Points. You click on that, that's going to fill in that location there. So let's systematically look. I'm not interested in picking up those, but I can fill the gap. Whoops. Fill the gap. I want trajectory point. Hold down the control key and select trajectory point and finish the line. Move along, following along the blue lines. Here we've got another section missing. Hold the control key down. And finish off that line. Scroll out. Work our way along. So we've got three almost in a row here. I wonder if there was some sort of a magnetic interference associated with it. Oops. Trajectory point. Trajectory point. Finish the line. Trajectory point. Trajectory point, finish the line, close the line, back out, scroll along, another section here missing, the point, hold the control key down, highlight the point and finish it. So I could add in some of this line section if I felt it was going to benefit our data. So this section through here hasn't been covered by this line, but then it's going to stop in the middle of nowhere. And we're over top of water, so there's really not a lot of point. So I'm happy with what I've got. If I turn off my trajectories, I can see what looks to be a nice continuous line. So now I'm ready to move on to the next piece. And the next step that we take is to create the trajectories. So if we click on this wizard, here we can see our post-processed trajectory file. So that's the output from POSBAC. And use the latest calibration file. So the TrueView gets calibrated, and we're just telling it to use the last one. So it was last calibrated on the 3rd of August 2021. We can ask it to retain photos in the layer with the flight lines, retain photos within the flight lines and interior turns, or retain all photos. So given that we got rid of a section, then I might say retain photos with flight lines and interior turns, because we've got such a curvy line. And I can ask it to update the photo EXIF tags immediately, rather than needing to do it as a separate process. So this saves me one step. Again, it's telling me that it's going to run the process. So it's reading the calibration, computing trajectory times, and now it's creating the trajectory line. It's going through and checking the images, reading the EXIF tags for all of the images, and then it's going to go through and update those EXIF tags. So 1,054 photos, and it's going through and building up the commands for each one, and now it's going to sit down, and you can see the pop-up. It's going through and updating the EXIF on each and every one of the files. You'll notice that these ones coming through now have an S. Some of the earlier ones had a P, and that's for port and starboard. So just like on a ship, you have a port and a starboard. Starboard being the right hand side, port being the left hand side. So now it's told me that it successfully created those trajectory files. It's retained the photo layer, and it's updated the EXIFs. So I can say OK. So now you can see we've got points here associated with the LiDAR and the port and starboard images. So if I keep zooming in, you'll see that we've got either one of the images. So they're not necessarily taken at exactly the same time. There's a fractional difference between the two of them. So now that I've completed that part of the process, so that was creating the trajectory. Now I'm going to geocode the LiDAR. So I'll tell it to geocode. I can do an angular clip of 40 degrees from LiDAR. Now I'm going to tell it to increase that to 60 degrees. So that will give us a bit more width. So some of our points are going to be a little bit on the oblique side, but as a point cloud that might only be useful. I want to enable the true track. This uses the roll angle to clip the relative to the NIDAR. So that's you'll have learnt through your lectures, pitch, roll and yaw. So this is taking care of the roll in order to try and get the points that are below relative to nadir. I can clip at a distance. So if I increased the in the config file, I could open up the LiDAR swath to become much wider, and that would take in the wheels or the legs of the drone. I could then put in and say, well, if it's within 3 meters of the drone or the LiDAR unit, then I don't want them, and I can clip to a certain distance, so I don't end up with all these scattered points miles away. I'm going to leave that as it is for now, and I can tell it to colorize the point cloud once it's finished the geocoding, so that's going to save me an operation or press of a button later. So I'll say OK and tell it to continue. So that is now completed. If I turn off the Google image, we can see our colorized point cloud. Now they've of course thinned it out, so there's a lot more points there than what we're seeing, but we can have a look at it in a 3D viewer. Let's just wait for it to withdraw. Let's draw my profile, and here it comes up in our data, in our viewer. And we can scroll along. We can use our zoom tool, zoom in or zoom out, increase the area under viewer. So here we go, we can see the top surface, picking up the edge of houses, some of the cars and the car park, but this is the area that we're most interested in. So let's have a look in the 3D viewer. So we can open up a 3D view just using this one here, and then I can put in an extent, and there's my 3D. Let's move to where the cliffs are a bit steeper. And here we can see quite well the formation of the cliff surface. So we have it in here as a point cloud. There's a number of things we can do in the software. Currently it's coloured in accordance with the RGB or the imagery. We can change it to colorize in accordance with elevation. So this is quite interesting here. If I come in and have a look, I can see that I've got this double back trajectory, and this is why we're getting all those extra points. So under normal circumstances I would probably go back, remove those extra trajectory locations to improve the quality of the data at the end. But for this particular case I think we're going to be fine. So I'm going to turn off that 3D, and we can also turn it into a tin. So we can see here we've got a surface, we've got our buildings. Given that these are on the extremity of the LiDAR, it's not surprising that they're not very accurate. And through here the tin just automatically tries to fill in the gaps between the points it's known. So if we go back to a point cloud, you can see we're missing data, but it just tries to interpolate that by doing it as a tin. So we've got our original point clouds, so I need to do some. So this section is about using Trimble Business Center to extract the control points that were collected using the GNSS system. So here's our project file. The first thing I needed to do was to set up my project settings. So I've set up the coordinate system to be GDA 94, zone 54, and using the geoid model Oz Geoid 09. So this is exactly the same as what we've plugged in for the LiDAR processing. So I've set up the project the way I want it, and I'll bring the data in. So now, because it's a slightly different coordinate system to what it was collected in, I'll tell it to keep the existing project definition, because I set that and I know that that's exactly what I want. So the points have now been brought in, and you'll notice that a lot of these have red flags. And if I open up the points, you can see that these have all come up with red, so there's an error. So I can have a look through here, identify the details associated with each of the locations. So if I want to have a look down here, you'll see there's a little red flag. If I click on that, it opens up a message window, and that's where I find out what's wrong with our data. So if I have a look at each of these points, it's telling me that the tilt distance exceeds the tolerance. So the tilt distance is the difference between the base of the pogo on the GNSS unit to where the rover unit is on top of the pole. So this is telling me that I've got a 5.34 centimetre or 53.4 centimetre millimetre error in my data. And as I scroll down, I can see that some of them is almost 10 centimetres. On top of that, we then need to add the anticipated error. So if I come down here, I can see that my horizontal precision was 1.1 centimetres. Add that to the 9.8 and all of a sudden we now have nearly 11 centimetre error. And in the vertical we've got at least 2 centimetres, and there'll be very slight difference in the vertical, but here it doesn't tell you what the vertical error is likely to be. It's only really looking at the horizontal, and there would be very minor difference between the vertical because of course if it's got a slight tilt on it, then the unit would be sitting fractionally lower, but it would only be millimetres. So now that I have become intimate with my coordinates, I know what sort of errors I've got. I could go through and document which one has what error, but for now I'm not necessarily interested in that. So I'm going to hit the export button and it's time to export it. Now I would usually export it into a file geodatabase so that it's easy to work in the GIS, but the software that we're using, the LP360, requires a shapefile or a text file. So I'm going to output it as a shapefile and make sure that I'm getting eastings, northings and orthometric height. So I give it a name and then I hit the export button. Now I already have this layer, so I'm not going to export it, but that's the process to export your coordinates for your ground station. So the first thing I need to do is I need to bring in a feature layer. So to do the quality control, there's a variety of different methods you can use, data sets you can use. I'm going to use a shapefile. You can also use an XYZ text file. So one of the things that you need to be aware of when you're using this particular piece of software is that it doesn't do on-the-fly reprojection. So we've gotten quite comfortable in ArcGIS where we can bring in layers that have got different projections and they just reproject on the fly. So there's a transformation engine inside of ArcGIS Pro that does the transformation process. In this particular piece of software there isn't. So I've got the points in now and I'll say OK, and you can see that my points are in green. If I turn the LiDAR off, you can see we've got some points up near the top and some points down low, and of course these were on the sand dune spit area. So now we've got some ground control that we can use to validate the data set that we've got.
Really.
So we want to change the symbol. The rest of them are all squares, so I'm going to pick something like a cross, and now they stand out much easier and much better. So before I start my quality control process, I need to get rid of these extra points that are going to be a problem for me. So I'm just going to delete them out of the data set so that we're only working with points that fit within our particular area. That one might and might not fit. So let's have a look at our quality control. Up here you can see we've got control points toolset, and we select our points layer. So this is our locations here. I am still a little concerned that these are going to give me quite poor errors. I also don't expect good data for over here where our control point was, because it's not in close to our flight plan. So I could just remove those two, but let's see what. When we come in, there's a choice between the different ways that we can process the data. We can use a tin triangulation, which in some cases would be fine, but given that our data is curved and we've got a lot of field gaps. But that doesn't seem a sensible way of going ahead. So we'll look at inverse distance weighted. Now it often comes up with a radius of something like 10 metres. I reset mine down to half a metre. So we can either run from the control XY or measured XY. We're going to use the control. And I could change the source points here. So I'll run that through. And as I suspected, our original marker, our base control, is around 5 centimetres out. But we're right on the edge. So these are all a couple of centimetres. We've got one here which is a standout, which is point number 7. So let's see where we'll save that. Let's see where point number 7 is. So we'll go to Feature Analyst and whoops, we'll highlight point number 7. And that's up here. So it's interesting, it's on the top of a cliff. Let's recolorize to our RGB. It's right on the edge of a walkway. So it's possible that minor misalignment between the two data sets means that it's picking up points that are around it rather than its actual location. So I'm not too worried about point number 7, even though it's come up with a high error issue. I come back in, I can have a look, rerun. Is there anything else worth looking into? So we've got another one here, control point 5 is 5 centimetres. That's still within our tolerance, but let's have a look at that one as well. So that's point number 5. Yes, let's save that. You've noticed it's created a measure points here. So point number 5. Where are you? So that's up here. So let's turn back on Google Imagery and turn off the point clouds. So we can see here it's in a bit of a divot. It's probably not the best place. It wouldn't be an issue just for photogrammetry, but it is a bit of an issue when you're coming to LiDAR because we're going for a half a metre circle around that particular location. So we're probably picking up a little bit of the vegetation. So let's see what happens if we run it again, but let's just try a 20 centimetre around. Now point 2's not found enough points, that's not an issue. It's not found enough points around our controls come up as significantly different. So our 0.7 is still about the same and our 0.5 is still about the same. Okay, so that gives us some confidence in our LiDAR data. So we now have a point cloud. We'll turn off the rest of these layers. And we've got it colorized. So the next thing I'm going to do is deal with the photogrammetry side of it. So the photogrammetry component is done through Metashape, so I can just send it through. So there's a Meta EVO there's an export package, and there's ortho photo from package. We don't need these two. We should be able to just run it straight and direct, so they're a bit of a legacy issue. So remember, we send out our aerial photos, so we're only interested in the retained photos. That gives us 783 to work from, and we want to generate an ortho, and let's have it generate a point cloud as well. If we've got an original DEM, then we could plug that in, or if we'd created a DEM off of our LiDAR points, then we could plug that one in too. So we now need to give it a new name. We'll call it Photo Layers. And our ortho image, we'll do it as clip face 2. Now we could go into some of the advanced settings. So use sensor fixed calibration, or let method shape do the calibration. We're going to stick with what we've got because we know that we have corrected it with the RTK. Point cloud, density and quality. So we could go ultra high, but that's going to make it take a lot longer. We could be aggressive. Let's just be mild. We'll create tiles that are 150 by 150. So the ortho we want to compress with LZW, and the background we'll leave as black. Include the alpha channels and optimize GSD for images. So we can now submit that. So this is now putting together a little package in the background and sending it off to Meta. You'll hear a ding in a minute because my email will pop up telling me that it's doing a processing, and under the job manager I can see that that one's in process and it's been started. Once it's finished doing the processing, we then do the post-process process, which then I'm not quite sure what it does, but I think it stitches it together into a nice ortho mosaic to go within here. So we can close that up, and now it's just a matter of waiting for the aerial imagery to turn up. So now I've received back the email from processing the imagery through Metashape, and you'll see that the icon over here on the left hand side is flicking to indicate that there's something that needs to be done. So we've finished the processing, so now we need to do the post-process. So this is going to set it up and bring it into our project that we can use underneath the existing data. So that's now complete, and I can close that. So if I turn off the LiDAR, we can see our high-res aerial imagery that's come off of the dual cameras from the bottom of the LiDAR unit. So now that I've got my aerial photography, I can start to have a look at how well our alignment is. So we ran some statistics previously and had a look at how well the vertical accuracy was, and it's certainly within our tolerance. Now I've got the aerial imagery in, I can zoom in and see how close we are. So remembering this is just corrected using the RTK base station, and so we've got a bit of a difference in distance, and so let's have a look at how far we are out. So if we take that centre and go out to here, so down in the bottom left hand corner, it took me a while to find where it was, we're looking at 5 centimetres. So that's certainly within the tolerance, and potentially that could be the tilt issue that we had on that particular marker. So let's go and have a look at another one. Zoom into this one, and I can tell it's roughly the same. We're looking at about 5 centimetres. So given that the GNSS is plus or minus 2 to 3 centimetres, and then we've got a tilt issue which was adding anything up to 10 centimetres, I'm pretty happy with the georeferencing that we've got in the data. I can actually turn off the aerial photo, and if we zoom out a little bit, we can start to see the impression of the target in the point cloud. So I'm fairly comfortable with this data. So now it's ready to be made available for students like yourselves to play with.